Hello student, welcome back. We are going to start today's lesson. It is lecture 11, module 4, microcontroller and embedded system. Shongita Roy, assistant professor, electronics and communication engineering department, Darula Institute of Technology. It is 11 and it is the continuation of lecture 10, PAL, logic structure. In order to illustrate the logical organization of PALs, we go back to our 3 input and 4 output example of the previous lecture. PAL implementation of the circuit. This circuit uses W, X, Y, and Z examples of the previous figure. Recall these examples are minimum realization for the output of our example. The PAL structure has a programmable AND plane and a fixed OR plane. So we should find the, yes, this is the programmable planes. So you have some idea, we have already studied this one. Yes. AND gate in the input and OR gate at the output. So ABC is the input and W, X, Y, Z the output. So PAL implementation is ABC is the input, W, X, Y, Z is the output. So it is implemented by using AND gate and at the output OR gates. Product term expansion. The limitation on the number of product terms per output in a PAL device can be overcome by providing feedbacks from the PAL output back into the AND plane. These feedback are used AND plane just like regular input of PAL. Such a feedback allows ORing a subset of product terms of a function to be fed back into the array of further to be ORed with the remaining product terms of the function. So PAL with product term expandability. So output is feedback to the input over there. 3-state outputs. A further improvement to the original PAL structure is done by adding 3-state control to its output as shown in the figure. In addition to the feedback from the output, this structure has 2 more advantages. First, the pin used as output or partial sum of product terms can also be used as input by turning off this 3-state gate that drives it. Note that the lines used for feeding back outputs into the input plane become connection from the IO2 input to the AND plane. The second advantage of this structure is that when IO2 is used as output, it becomes a 3-state output that is controlled by a programmable product term. Instead of using a 3-state inverting buffer, an XOR gate with 3-state output and a fusible input provides output polarity control when the bidirectional IO2 port is used as output. So this is the figure output inversion control. Registered output. A major advantages of PALs over PLAs and ROMs is the capability of incorporating register into the logic structure. Where register can only be added to the latter two structures on their input and outputs, Register added to the PAL array become more integrated into the input and output of the PAL logic. As an example structure, consider the register output of figure. The input output shown can be used as a registered output with three state as an two-state output as the registered feedback into the logic array or as an input into the AND plane. So output inversion control. So this is an example. A further enhancement to this structure provides logic for bypassing the output flip-flop when its corresponding I/O pin is being used as output. This way, PAL output can be programmed as registered or combinational pins. Other enhancements to the register option include the use of asynchronous control signal for the flip-flop, direct feedback from the flip-flop into the array, and providing a programmable logic function for the flip-flop output and the feedback line. Commercial parts. PAL is a trademark of American Micro Device Corporation. More generally, these devices are referred as PLDs or programmable logic devices. A variation of the PAL or a PLD that is somewhat different from a PAL is JAL, General Array Logic. The inventor of JAL is the Lattice Semiconductor Corporation. JALs are electrically erasable, otherwise have a similar logic structure as that of PALs. By ability to bypass output flip-flops, JALs can be configured as combinational or sequential circuits. To familiarize readers with some actual parts, we will discuss in Altera part. Altera Classic EPLD family. Altera Corporation's line of PLDs is its classic EPLD family. These devices are EEPROM based and have 300 to 900 usable gates depending on the specific part. These parts come in 24 to 68 pin packages and are available in dual inline package DIP, plastic J-lead chip carriers PLCC, or pin grid array PGA, and small outline integrated circuit SOIC packages. The group of product terms that are ORed together as referred to as macro cell, and the number of macro cells varies between 16 to 48 depending on the device. Each macro cell has a programmable register that can be programmed as a D, T, JK, SR flip-flop with individual clear and clock controls. These devices are fabricated on CMOS technology and are TTL compatible. They can be used with other manufacturers' PAL and JAL parts. The EP1810 is the largest of these devices that has 900 usable gates, 48 macro cells, and maximum of 64 I/O pins. Pin-to-pin logic delay of this part is 20 nanoseconds, and it can operate with a maximum frequency of 50 megahertz. The architecture of this and other Altera Classic EPLDs include macro cells, programmable register, output enable or clock select, and a feedback select. Macro cells. Classic macro cells can be individually configured for both sequential and combinational logic operation. 8 product terms form a programmable AND array that feeds an OR gate for combinatorial logic implementation. An additional product term is used for asynchronous clear control of the internal register. Another product term implements either an output erasable or a logic array generated clock. Inputs to the programmable AND array come from both the true and complement signals of the dedicated inputs. Feedbacks from the I/O pins that are configured as an input, and feedbacks from the macro cell outputs. Signal from dedicated inputs are globally routed and can feed the inputs of all device macro cells. The feedback multiplexer controls the routing of feedback signals from macro cells and from I/O pins. The 8 product terms of the programmable AND array feed the 8 input or OR gate, which then feeds one input to a XOR gate. The other input to the XOR gate is connected to the programmable bit that allows the array output to be inverted. This gate is used to implement either active high or active low logic or De Morgan's inversion to reduce the number of product terms needed to implement. Programmable registers. To implement register function, each macro cell register can be individually programmed for D, T, JK or SR operation. If necessary, the register can be bypassed the combinational operation. Register have an individual asynchronous clear function that is controlled by a dedicated product term. These registers are cleared automatically during power up. In addition, macro cell register can be individually clocked by either a global clock or by input or feedback path to the AND gate array. Altera's proprietary programmable I/O architecture allow the designer to program output and feedback paths for combinatorial or registered operation in both active high or active low modes. This is the Altera Classic microcell example. Output enable or clock select. The box shown in the upper part of the figure allows two modes of operation for output of clock of classic microcells. Mode 0. The tri-state output buffer is controlled by a single product term. If the output enable is high, the output buffer is enabled. If the output enable is low, the output clock a high impedance value. In mode 0, the macrocell flip-flop is clocked by its global clock input signal. In mode 1, the output enable buffer is always enabled and the macrocell register can be triggered by an array clock signal generated by a product term. This mode allows register to be individually clocked by any signal on the AND array. With both true and complement signal in the AND array, the register can be configured to trigger on a rising or a falling edge. This product term control clock configuration also support gated clock structures. So this is the macro cell OE or clock select. Upper is mode 0, lower is mode 1. Feedback select. Each macro cell in a classic device provides feedback selection that is controlled by the feedback multiplexer. This feedback selection allows the designer to feed either the macro cell output or the IO pin input associated with the macro cell back to the input AND array. The macro cell output can be either the Q output of the programmable register or the combinatorial output of the macro cell. Different devices has different feedback multiplexer configurations. EP1810 macro cell can be either two feedback configuration, quadrant or dual. Most macro cells in EP1810 devices have a quadrant feedback configuration. Either the macro cell output or IO pin input can feedback to other macro cell in the same quadrant. Selected micro cells in EP1810 devices have a dual feedback configuration. The output of the macro cell feeds back to the other macro cells in the same quadrant and the IO pin input feeds back to all macro cells in the input device. If the associated IO pin is not used, the macro cell output can optionally feed all macro cells in the device. In this case, the output of the macro cell passes through the tri-state buffer and uses the feedback path between the buffer and IO pin. So this is the classic feedback multiplexer configuration. Complex programmable logic devices, CPLD. The next step in the evaluation of complexity of programmable devices is the CPLD or complex PLD. Extending PLDs by making their AND plane larger and having more macro cells in order to be able to implement larger and more complex logic circuits would face difficulties in speed and chip area utilization. Therefore, instead of simply making this structure larger, CPLDs are created that consist of multiple PLDs with programmable wiring channels between PLDs. So this is the CPLD block diagram. There are different PLDs with a line of IO cells, programmable wiring channels. Macro cells. The MAX 7000 macro cell can be individually configured for either sequential or combinatorial logic operation. The macro cell consists three functional blocks: the logic array, the product term, select matrix, and the programmable register. The macro cell for EPM 7128S is shown. This is a MAX 700128S macro cell. So we are ending the session over there. These are the references, and thank you. We are ending the session.